Yeah.
I can't catch you guys with that anymore. It's fun while it lasted.
What? Do that every year, like first day they tell me class, like ready for the quiz.
Well, we did have a quiz the first day, so that wasn't a bluff. But yeah, I try to catch them throughout the semester. Hey, okay. So we're started. Okay. So I believe we have homework due today.
What homework?
It doesn't work on me. Oh, come on. 6.2.
That's a lot. 36. 35. There's a whole lot.
What was it?
0, 5, 0 to 5, 6. Radical 1 plus cosine 2.
Radical of 1
Plus cosine 2x.
cosine 2x.
That's it.
That's it.
Dx. Okay. Who tried it?
You can multiply by 2 and then make it cosine squared x.
No, use the half angle formula to change cosine 2x into sine.
Okay, right. So I'm not. You can't just multiply something by 2, right? It's not an equation. So
since you would divide by 2 normally, to do the opposite. I forget.
Not sure what you're saying. Okay, so you want to use the half angle formula here. What formula do we use there?
2 plus squared x minus 1.
What?
2 plus squared x minus 1.
You want 2 cosine squared minus 1. Perfectly valid. This kills that. So we just have radical 2 times the integral of 0 to 6. And now we have cosine squared x here. Right? Now remember, technically this is the absolute value of cosine x, but because we're on an interval where cosine is positive, we can just cancel here. So it's really just, this is just that guy in disguise, basically. Now what? What's the integral of cosine? Sine x, and we integrate, we evaluate between pi over 6 and 0. Sine of pi over 6 is a half. So you get radical 2 over 2. Sine of 0? That's your answer. Yeah, so here you saw this. It might have looked confusing before, but then you start going through your options. Obviously you can't use the power rule, which is the first thing you always think about. And you wouldn't use substitution because you need the sine, a factor of sine 2x somewhere. So you think, what else could I do? Well, trig identity is what you'd think of. And
you wouldn't change the limits for this, right?
no, I didn't do a substitution. Changing the limits is a non-issue. Yes? Sure. What? The integral of cosecant. So that one, we think they figured out that one. You just remember it. What?
Is like the other one we did.
It's very similar to secant. Exactly. You sort of do this trick.
Multiply by cosecant minus cotangent.
Right? Don't ask me how they come up with this stuff, but it works. Right? So now you have cosecant squared x minus cosecant cotangent. Right? And what do you do now? U equals the denominator. Substitution. Derivative of cosecant? It's minus cosecant cotangent. Derivative of cotangent? Cosecant squared. No, this. we have a minus?
Yeah.
Okay, so now when you start to plug this in, what does it look like? It looks like just the negative of that one. All right? So we can become minus 1 over u du.
Yeah, there's
There's,
it's like secant.
It's cosecant x plus cosine x over cosecant x plus cosine.
It just-
We don't need a minus.
yeah, I don't, why,
No.
that's not,
It's a minus.
It's a minus over there.
It
The
just-
whole function
It's-
is gonna be.
Communicative. That's communicative.
Wait.
right, it's the same thing, okay. 'Cause who's telling me minus? Okay, so it's just 1 over u, so this is ln u plus c. So we get ln of this guy, cosecant x minus cotangent x. Other questions?
Yeah. For this.
Hmm?
So if we use plus, cosecant x plus cotangent x, we got answer is negative ln. Can you write it?
If it was cosecant plus here,
If that is,
Yeah, we use a plus.
if we use a plus,
Cosecant.
we got answer is negative ln and cosecant x plus cotangent.
He's saying to use a plus in between, like cosecant minus cotangent is like cosecant plus cotangent.
oh, put plus here and plus here,
Yeah.
and then you did it, you get a negative?
Can you write the answer?
Yeah, it'll be fine.
Is it negative? My question is not this. Is not this. But first, can you write it?
You want me to do it with? So-
Like secant, you multiply plus, right?
You multiplied by cosecant x plus cotangent x?
Yes.
That's what you did? And what actually happened here?
And cosecant squared.
Right, so on top you have cosecant squared and cosecant cotangent, but then you would have what? Your u is this? Your du would be what?
Cosecant cotangent. Negative.
Minus cosecant x cotangent x.
Negative. Minus cosecant squared.
But and factor out the negative.
And this factor out negative.
That's another way you can do it, I guess.
Okay. So you factor out the negative.
Negative du.
And then substitute dx.
Right, so ultimately what would the answer look like?
Negative
ln cosecant
cosecant x plus tan x.
x plus cotangent x.
Did we, is that different from what we had before?
That is true. And my question is, how can these two, how to change each other?
Well, you tell me, what do you think you would do?
Now my question is, how to change that to that, into that?
How would you change this? Is there something wrong here, or?
There's lots of powers, right? So we just bring the minus in. So one over cosecant is. No.
Is that right? Is something wrong? Can we change one to the other? Because remember last time we actually spoke about this, how sometimes you can have an integral where the answers look different, but they're the same. Is that what's going on here, or is something else?
No, that's something else.
What's wrong?
First, this answer in your syllabus.
Yeah, which means they're the same. How do you transform one into the other?
How to transform?
Well, what would your idea be?
Bring it to the power.
Right, just bring this up here. That becomes the inverse. Fiddle around with it, you'll get it. Other questions?
13. The integral of cosine squared x, tan cubed x, dx.
That one?
So you have cosine squared x and then tangent cubed x is the same thing as sine cubed
Yeah,
x.
that one's actually not so bad. That one you just,
Split it down.
right, tangent is sine cube over cosine cube.
That cancels the cosine.
This will cancel with one of those, and then what?
And you have sine squared times sine x over cosine.
Pretty much take u as cosine. Yeah, and just solve that.
Right, so if you take u as cosine x, your du is minus sine x dx, which gets rid of one of the signs, but we have three factors of sine here. So you just think of this as sine squared times sine, and you break this into 1 minus cosine squared, right? So you end up with minus the integral of 1 minus u squared du over u. And so now you just split the integral up, right? So it's just 1 over u minus u.
Here. Integrate.
So this gives us what?
Half of cosine.
This is ln u. There's a minus sign on the outside. Minus u squared over 2. Plus c. And now you just replace your u with cosine. So this is minus ln of cosine minus cosine squared over 2. Other questions? Probably have time for a couple more.
31. The integral of cosine 5 theta.
Cotangent fifth power,
Yeah, fifth theta. Cosecant of 3.
cosecant
To the
cube.
third, yeah. And it's from pi over 2 to pi over 4.
All right, how do we do that one? Huh?
It's split pi. It's pi over 4 to pi over 2.
Who did that one? What did you try? You rewrote this as cotangent to the fourth. Cosecant squared. And then cotangent cosecant. Okay. Then what? Identity where?
First, cotangent squared and the
Right, you think of this as cotangent squared squared. And what's the identity that links cotangent and cosecant? Okay, now what? U equals cosecant negative cosecant cotangent. And so we end up with, of course, there are still limits on this over pi over 4, pi over 2, pi over 4, pi over 2. Do you guys want to change the limits or keep them? Let's just keep them. So theta goes from pi over 4 up to pi over 2. We'll just swap back and then plug in the thetas then. And we have u squared minus 1 squared times u squared du. What's this? U to the fourth minus 1, right?
I think we have to swap one negative.
The negative, yeah. This is just u to the fourth minus 1? I wanted someone to say yes so I can just throw my chalk at them. So what is this? That is a blasphemy, yes. You write u to the fourth minus 1, you get 0 on the test, exactly.
Oh, on the question of the test.
The test. This is one of the test-wide blasphemies. Okay, so then what? 2u squared times u squared minus sign, don't forget the minus sign. Theta is pi over 4, pi over 2. U to the 6 minus 2u to the 4th plus u squared. At this point, it's just going through the motions. You just go on autopilot at this point. And we can integrate now. So u to the 7 over 7 minus 2u to the 5th over 5 plus u cubed over 3. Remember, this is our theta that's going from pi over 4 to pi over 2. So now before plugging them in, you can't plug them into the u because they're not the u. You're going to do back substitute. So replace your u with the cosecant. So this is cosecant to the 7. Were you raising your hand? No. Oh, you were stretching? What?
You can look behind your back.
I can tell when someone's raising their hand. It's a, you know, you teach after so often, you're like, someone's raising their hand right now, I can feel it. You left it like that. Forget it. What's cosecant of pi over 2? What's cosecant? 1 over sine. What's sine of pi over 2? Are you just messing with me? You really want me to throw this, don't you? That's 1. This is just going to be 2/5. This is going to be 1/3 minus, and this is going to be the ugly part.
Yeah, I stopped there.
Well, it's not super bad. You know, what's sine of pi over 4 is? Radical 2, or you can think of it as 1 over radical 2, it flips and becomes radical 2, so this is like radical 2 to the 7 over 7 minus 2 radical 2 to the 5 over 5 plus radical 2 to the 3 over 3, and then we give up. Stopping here is too soon because I need to know that you know what the value is at the special angle.
It's okay to live like that, right?
We'll only take off 1 point. You do this, I'll take off half the points. You guys have to know trig, it's important. We've actually seen that already. So that's that. Move the pass the homework to the front.
Wait, how do you know when to change the limit?
It's a personal preference. You can change limits if you choose to.
But how would make
Some
it
people
allow
don't
you
like.
to do exactly?
Except, remember, when it's trig sub, always change the limits, right? Never do a definite trig sub integral and then decide to back substitute. You're wasting time. What's the problem?
It was one of the last ones.
What is that? But completing the square is algebra. We're how about this though? How would you do that?
Don't.
Skip it? It's not an option.
Isn't that like power? No. No, the power's model. Yeah, no.
How do you do it? A trig sub? How would a trig sub work? Can we do a trig sub here? No, we can't. Why not? You do have the right form. You have to have an x squared, right? You have to have that quadratic form going on. So a trig sub is not an option, thankfully. How would you do it? You try by parts? Why'd you jump so far? See a random integral, what's the first thing you think? Well, technically that's the second thing. First thing you think, can I simplify and use the power rule? No. Okay, what's the second thing you think? Substitution. Now when you think substitution, you think, what would I substitute? If you wanted to substitute something, what would you substitute? The x plus 2. Alright, so let's go with that. Then what? du equals dx, okay. What happens now?
X plus 1 is u.
There's that x plus 1. How do we deal with that x plus 1?
U minus 2 equals.
Right. From your substitution, remember we looked at cases where we actually did this. You just solve for u minus 2. That gives you the x. Which means if I can add 1 to both sides to get x plus 1. Right? So this guy actually becomes the integral of u minus 1 times, this is just u, so this is u to the 1/3. Right? And from there it's trivial. Right? I was just wondering. Someone asked me this in the tutoring center today, and I wondered, could my kids do that? Decided to ask you guys. Okay, now we're getting down to, we're going to segue into the actual topic of today with one of the problems I put on the bonus on the last quiz. I believe it was something like this.
Yeah, those aren't really bonuses. They're not.
That was a bonus. Come
It's
on.
like things you can't do.
Yeah, exactly.
You can do it. Did anyone have an idea of how to do this? Huh?
Making the A to C like A to B, and now just look at the
You just read it into the part of the practice. Did anyone actually attempt anything?
No.
I have no time.
Yeah.
There are a couple ways you can do this. I'm going to show you a couple. The first way is, yeah, simplify with long division. I'm going to talk about when you want to do this in a second. But does anyone remember how to do long division? I did tell you guys to look it up. How do you actually do long division?
Yeah.
like a
So you have x squared plus 1 out here. You have x squared plus 0x minus 1. Remember, you need the placeholders. You need things to line up. And then what?
1.
Right, you take the first guy into this, goes 1 times, you take that 1, you multiply everyone here. So 1 times x squared is x squared, 1 times 1 is 1, line it up with the 1, and you subtract this guy, right? So this dies, you have minus 1, so you end up with minus 2.
That's your remainder.
X squared cannot go in there, that's the remainder. So this guy is actually what? 1 minus 2 over x squared plus 1. Right? Can we deal with that integral? Integral of 1? X. Integral of this? The tan thing. Minus 2 tan inverse. Ah, see? Wasn't that bad? That's a fair bonus problem, I think. So long division was one way to think about it. An equivalent way, but something that you might see easier for some of you. When the powers on the top and bottom are the same, you can sort of do this trick. I mean, if you get it and it resonates with you, great, use it. If not, just do the long division, it's fine. But for some people, you might think it's quicker. The trick is, when you have the top power and the bottom power the same, what you can try to do is get the denominator in the top. Right? What do I mean by that? The denominator says x squared plus 1. Try to get an x squared plus 1 in the top. How would I do that? X squared plus 1 minus 1. Exactly. So I go x squared plus 1 minus 1. Right? This simplifies to what? You have x squared plus 1 minus 2. You see where I'm going with this? You can split the fractions now, right? Oh. Right? X squared plus 1 over x squared plus 1 is 1. 2 over this. Right? See, it is sneaky, but it's cool. Right? So, tricks like these are the ones I use in my head, you know, and They come in the tutoring, so how do you do this integral? Oh, that's just x minus 2 tangent over. How do you know that so quick? Right? I did this in my head, and they're trying to go think, how do you do the long division in your head? I didn't do long division. Okay, so this is going to be the segue into the topic of today, which is 6.3, partial fractions. It's another integration technique. It's pretty cool. And there are going to be cases where we can get away with a lot of stuff using partial fractions. I will show you in a bit. But let's sort of go over the idea first. The idea behind partial fractions is basically the idea I just erased, right? You get something that's a rational function, right? You have a polynomial over a polynomial. What you do is you kind of break that fraction up into smaller pieces that you can actually deal with, right? That's the idea behind a partial fraction. So let's look at something like this. X squared minus 5x plus 6. Okay. Just to make sure you guys are keeping up with your studies. How do you do this without partial fractions? You can do it without partial fractions. How would you do it? Trig sub? How would a trig sub work here? Complete the square. Someone asked about. Okay, so without trig sub, what's the complete square of this?
5 over 2 squared plus minus, so it's x squared minus 5x plus 5 over 2 squared.
Right, so it's going to be x minus 5 over 2 squared, right? There's going to be a minus 5 over 2 squared here, plus 6. What do I get? I'd get 25 over 4? What would I get?
Give me slowly.
You go x squared minus 5x, you add half the coefficient of x, square it, minus half the coefficient of x, square it, plus 6, right? The first 3 become the complete square. You take x and the guy inside the brackets, that's your complete square. On the outside, you combine what's left. Here you have 25 minus 25 over 4 plus 6. What do you get? Minus 25 over 4. 6 you can think of as 24 over 4. So you have minus 25 over 4 plus 24 over 4. You get?
1 over 4.
Minus 1 over 4, which you can write as 1/2 squared. And now you see how you do it with a trig sub? Right, so at this point, you can say x minus 5 over 2 equals, what would be the trig sub? It's not just secant.
1 over 2. No, what is A? The A is 5 over
1 over 2 secant theta. Right? Remember, it's the A secant theta. The A in this case is 1/2. Right? And then you do that, it would be insanely annoying. So I'm not going to continue. But there's actually another way about this. What if you knew a priori, but suppose we knew by some stroke of luck that is true. Is that? Yes. Right? That's actually true. You can check it if you want. I'll actually show you how to figure that out in this section. But suppose you did know that. Pretend you did know. Now how would you do this integral? Replace it, right? How do you do that? Easy, right? Easy if you knew this, right? So now the question is, how would we know that, right? That's where partial fraction comes in. So the idea is a partial fraction is sort of reversing a combination of fractions. So by going in this direction, what you're doing is you're combining the fractions. Right? You can actually add these two fractions, and then you combine them, you'll get that fraction. But going the other way, if you started here and you come to here, that is called a partial fraction decomposition. Basically, breaking up a larger fraction into smaller ones. Wouldn't it be great if we knew like a straightforward method how to do that? Okay, let's actually do it. It turns out that there is a method to get from this point to that point. It is straightforward. It's not always easy. It depends on the problem, of course. Not always easy, but it is straightforward. There are a sequence of steps that you can take that you pretty much always perform in the same order in order to go from something like this, which is complicated, which without this technique you'd use a trig sub and you'd spend like 5 pages and 2 days figuring it out, to go in something like this where you can pretty much look and know what the answer is. So what I'm going to do now is I am going to actually tell you this method, which is so nice. By the way, things you'll need to know for this section: long division of polynomials, it will come in handy. How to factor polynomials, and how to solve simultaneous equations. Once you know that, you are good enough to do this method. So let's actually talk about that. The method of partial fractions. How do you break up a larger fraction into smaller ones? As it turns out, factoring is not the first step. So given p of x over q of x, p, q are polynomials, q not 0, of course. We might be able to break it up into smaller fractions by to break it up. Step 1. What do you think step 1 is? Remember the example I did just before I started this, talking about this section? Not completing the square. You have to check the powers. Check the degrees. Remember what a degree is? What's a degree? Degree of a polynomial. The thing on top. What?
That's another fast one.
The highest power, right? The highest power, right? So a quadratic has degree 2, linear function has degree 1, etc., right? I also told you guys to look that up, right? Check the degrees. If the degree of p is greater than or equal to the degree of q, right? Then what do? Long division. Or one of the trick I showed you, or algebraic manipulation. To break it down. Degree of p must be less than the degree of q for this method to work. Right? So an example is like the one I told you before, right? So if you have something like this, you wouldn't really do this method, you just do the long division, right? And see what you get. You might have something nice that you can work with, you might have to break it down further. But understanding that the degree is higher on the top or the bottom, so if it was a cubed and we still had a square down here, again, you wouldn't jump into the method of partial fractions. You always try to simplify first. You need the power on top to be smaller than the power on the bottom. That's very important. The method will not work unless that's true, right? Degree of p must be less than the degree of q for this to work. Otherwise, partial fractions will not work, right? So the first thing you're going to do is look at your highest powers, right? The highest power must be on the bottom for partial fractions to work. So that's step one. And a lot of the times you realize, just as with this guy, once you do the long division, you don't really need to do anything else. It turns out easy after that. Okay. Step two. What do you think step two is? Red there ahead. So once you know that the degree of p is actually smaller than the degree of q. Yes?
The degree of p has to be greater than q to do long division, but that means that it can't work if it's less than q.
Yeah.
If the degree of p is
If the degree of p is bigger than the degree of q, then do long division.
You have to do long division, not this one.
Yeah.
The other one.
The box.
Like this is an example. Right? Here the degree of p is 2, the degree of q is 2. It's equal. So what we did was we did a long division. Right? Or if this is a cubed and that's a square, again, you do a long division. Right? You try to simplify it first. Okay? The degree of p must be less than q for this method to work. Right? So if that's not the case, you don't do this. You simplify
Power
first.
on the top.
You need the smaller power on the top. Right. So, in step two, now let's pretend that we know the smaller power is on top. What do we do next?
Factor the denominator.
Factor the denominator completely. That's the second step, which is a step on its own, factoring. Step 3. How do you, at this point is where you start to break the fractions up. How do you think we break them up? Break up the larger fraction into smaller fractions. Whose denominator are the factors from step 2. So let's do an example. What do I mean? Like the first one I did, x squared plus minus 5x plus 6. The degree of the top is 0, the degree of the bottom is 2, right? So the smaller power is in the top, we're good. So we can skip step 1. Step 2, factor the denominator completely, right? So what do we do? X minus 3, x minus 2 was the next step, right? So this here is step 2. And now what you do is you sort of break this up into 2 fractions, right? Where each factor here gets to be a denominator, x minus 3, x minus 2. Right? So this is step 3. Good. Make sure the top has the smaller power. At that point, factor the denominator completely. What happens if the denominator does not factor? Like you're stuck doing something else, complete the square and do a trig sum, you're stuck with it, right? We have to be able to factor the denominator for this to work. So, okay, check the degrees. Okay, degrees work out, factor the denominator. Once you factor the denominator, start breaking the fractions up across the denominators, right? Notice that I left off the top here. I have to actually talk about how to fill in the top. Did you guys get this? One caveat though, if the denominator has a repeated factor, so it's hard to describe this in words. I'll just show you what I mean by count up. So let's say you had a fraction that looks like this. Right? You factor the denominator and you get this. How would you break it up? So there's an x here.
X plus 1.
X plus 1.
And then x plus 1 squared.
X plus 1 squared. Right? See here, the power was a 2. I have to count up to the power. I just repeat that factor until I get to the power. Or if I had p to the x over x squared, x plus 1, x minus 4 cubed. How would I break that up?
X, 5.
First denominator is x, the second one?
X squared.
X squared, third one?
X plus 1.
X plus 1, fourth one? X minus 4, x minus 4 squared, x minus 4 cubed. Right? That's how you'd break it up. Okay? The method is long to work out, but once you practice a couple problems, it'll sort of be streamlined, right? So the first step, check the degrees. If the degree on top is greater than or equal to the degree on the bottom, simplify. Do long division, do algebraic manipulation, something. Get to step 2, you factor the denominator completely. If this happens, great, you can do partial fractions. If it doesn't happen, you need to do something else. Step 3 is to break up the fractions. You break it across the denominator this way, across each factor. If a factor is repeated, you count up to the powers. Okay? So this is we're building up to the smaller fractions here. Okay. Can I erase this? Step 4. Notice that I left off the numerators. There's actually a method of how you write the numerators. So I'm going to tell you about that next, right? After this, we're going to do some complete examples so you can see it all in like one thing. But after each step, I'm just going to illustrate. And then we'll do it all at once. Step 4. So we are at the stage now where we broke up the fractions into several smaller fractions. We know exactly what the denominators look like. They're just the factors of the original guy. How do the numerators look? ABC. Is it always ABC? Fill out the numerator according to this rule. It must be a general polynomial that is 1 degree less than the factor in the denominator. What do you mean, Jhevon? Okay, I'm going to tell you. Don't worry. Glad you asked. Let's do some examples. I factored a denominator, and it looks like this. All right, let me start easy. Yeah, geez, Jhevon, you're OD. Okay. I factor of the denominator looks like this. Okay? So we went through step 1, the degrees are fine. Went to step 2, factor the denominator. Go to step 3, split these guys up. Now we're on step 4. How do I fill in the numerators? What's the degree of the bottom? 1. So the degree of the numerator must be what? 0. You must be 1 degree less. Specifically 1 degree less. Exactly 1 degree less, right? So if you're a linear polynomial, what does a 0 degree polynomial look like? It's just a constant. We normally denote it with a capital letter, like A, plus B. Okay. Let's do some more variations. I just wanted you guys to see how we break this up. Okay, so I have a random polynomial. Let's say now let's jump to my second example. How would you break that up? Denominator is x. Another denominator is x squared plus 1. What goes on top here? A. Bx plus c. Do you see why? The degree of the bottom is 2, which means on top I need to write degree 1. Right? A degree 1 means it has to have an x to the first power and a constant. And remember, I write the general polynomial. So don't just write bx. You need to have the c, right? You have to. The c doesn't have to be 0. It can actually be a number. So you write the general polynomial. Another example. How would I break that one up? X here. Here's x cubed plus 7, which doesn't factor nicely over rational numbers. What goes on top here? What goes on top here? Bx squared plus cx plus d. Right? The bottom is a cubic, which means the top has to be a quadratic. The top is always 1 degree less than the bottom. Another example. How would I break that up? X
squared. X plus 1. X squared plus 2.
What goes on top here?
A.
What goes on top here? Ah, gotcha. You don't need it here. You only watch the inside factor, right? If it's a repeated factor, you watch the inside. There's a reason for that, but we don't really need to know it. Right? You can actually do the algebra. X was the factor, right? So we look at the x, right? I can show you why, but I don't have board space and board real estate is slim right now, right? So you watch the inside factor, it's just a b. You think of the factor as x, right? It's just that it's repeated, right? When I talk about factors, I'm talking about the base. What goes up here? C, just a 0 degree. What goes up here? Bx plus e. We have to know our alphabet now. Let's go up to F, G, H, G. Let's do another example, just to see if you know how to break it up. P of x over x plus 1, x plus t squared, x cubed plus 1. There's a trick in this one. I'm not going to tell you what it is. What's wrong here? Nothing's wrong. Jhevon, you wouldn't tell us the wrong thing. It's not factored completely. We can't actually factor x cubed plus 1, right? This is actually what? X cubed plus 1 factored is what? It goes into x plus 1 times
x squared
minus x So what we actually have is x plus 1 squared, x plus 2 squared, times x squared minus x plus 1. How do we break that up? What goes on top? That's your alphabet? A. Whatever is after E, right? Are we getting it?
Yeah.
There have been times when a final has asked us to actually just break up a fraction into its partial fractions, and you don't need to find what the A, B's, blah, blah, blah are. In general, though, we do need to find it, so I'm actually going to show you how to find it. Right? But this is sort of the idea. This is how you sort of understand what a larger fraction looks like as a bunch of smaller fractions. Right? That's how you sort of break it up. What step are we on? Step 5 would be to solve for the, we call them arbitrary constants. Using that's basically your step 5, is to solve. I'm going to tell you the methods. There are a couple. The first one I prefer to use first, if at all possible. And then the second one can help us out, or you can use it all the time if you'd like. Okay, so let's actually do an example. Okay, let's talk about the two methods. Method 1. Has 2 steps, I think. I can write down as 2 steps. Step 1, multiply both sides. I'm going to do an example at the end. Multiply both sides by the denominator of the original fraction, the original big one. Step 2, plug in convenient values of x to solve for each constant. By convenient values, I mean values that make most terms 0. So let's actually see what I'm talking about when I say that. So let's do method 1 on the very first fraction, the very first example. So I'm given this guy, 1 over x squared minus 5x plus 6. And you're like, I don't want to do a trig sub on that one if I have to integrate it, so how do I actually break it up? Right? You can notice that the denominator factors, right? So you would factor this. This is equal to 1 over the factors. X minus 2 times x minus 3, right? How do we break this up? A over x minus 2, b over x minus 3, right? We're now at the last step, basically. Right? Now at this point, you can employ method 1, right? what does method 1 say? Multiply both sides by the denominator over here. All right? So I'm going to multiply this whole thing by x minus 2, x minus 3. What's going to happen on this side? Just becomes 1. What happens on this side? X minus 2 would cancel. I would just be left with x minus 3. Plus
B times x minus 2.
b times x minus 2, because the x minus 3 would cancel, and I'd just be left with x minus 2. Right? So now we're here, and now we can do step 2. We're going to plug in convenient values of x. What do you think a convenient value of x would be? 3 would be a convenient value, because that will make this 0, and I can solve for b. So I can plug in x equals 3, and then what's my equation? It'll just be 1 equals b times 3 minus 2. In other words, 1 equals b, right? Equals 1. Go back here. Can you think of another convenient value? 2. If we plug in x equals 2, we get 1 on this side. This guy won't die. I would have a times 2 minus 3. But this guy, 2 would kill it. I'd get 0. So I'd only have a. In other words, I have minus a equals 1, which means a equals minus 1. So what do we end up with? I end up with the fact that 1 over x squared minus 5x plus 6 is equal to, the a is a minus 1. So I can put a minus 1 here. Plus the b is a positive 1. Positive 1 there. Which, if I know this is that, and I have to integrate it, then it's easy. So you see how we went through all the methods. So went here, and we're like, okay, the degree of the top is 0, the degree of the bottom is 2, everything's good. Move on to the next step. Factor the denominator completely. Move on to the next step. Break up into smaller fractions. Make sure that the tops are 1 degree smaller than the bottoms. At that point, multiply through by the denominators and plug in convenient values of x to solve for the constants. That's method 1. There's another method that we can use, method 2. Sometimes you might have to use a mixture of the two, because there are some times when the equation here, there's nothing you can plug in that will make most people 0. It happens. So at that point, don't get stuck. You can do something like method 2. Method 2, step 1. Same as in method 1. Right? Multiply both sides by a denominator of the left side. Step 2. Multiply out the right side. And combine like powers of x. Step 3. Equate coefficients of like powers of x to set up simultaneous equations that we can solve. Okay, let's see method 2 in action. Let's do it on this same one so you can compare. Did you guys get this?
Yeah.
So let's do method 2 on this guy. So you realize that this is just x minus 2, x minus 3. We break this up into a over x minus 2 plus b over x minus 3. Multiply both sides by the denominator on the left, we get 1 is equal to a times x minus 3 plus b times x minus 2. Right? So at this point we're at the same place as in method 1. But method 2 goes a little bit differently. We're going to multiply out the right side, right? Expand the brackets in other words. So this would be ax minus 3a plus bx minus 2b. And then we're going to combine like powers of x. We're going to group the like powers of x. So I have x to the first power. Let's group those together. I have a plus b times x to the first power. That groups all the x's together. Now I have x's to the 0 power, just the constant terms. I can group those together. Minus 3a minus 2b. Right? So I group all the guys with x's, group all the guys that don't have x's. Right? If I had x squares, I'd group all the guys with x squares, group all the guys with x cubed. Right? You group them all together. Now what you do at this point is step 3. You equate the coefficients of like powers. By equate coefficients, I mean the coefficient, if this is an equal sign, the coefficients on this side must be the same as coefficients on that side. What's the coefficient of x on this side? 0, right? You can pretend there's a 0x here plus a 1. So the coefficient of x on this side is 0. The constant term is a 1, which means a plus b must match up to 0. This guy must match up to 1. And I can set up a set of simultaneous equations. I know that a plus b must be 0. I also know that minus 3a minus 2b must be 1. So now I have a set of simultaneous equations. I can solve that, right? So this is equation 1, this is equation 2. Notice in 1, there are a bunch of ways you can go from here. You can do the substitution method, you can do the elimination method. I don't know. It really doesn't matter. I can do 3a plus 3b equals 0. This is just 1 times 3. Then I can add these two. A's would die. Here I have b equals 1. Plug into 1. I would get a plus 1 equals 0, which means a equals minus 1. Which means ultimately that 1 over x squared minus 5x plus 6 is minus 1 over x minus 2 plus 1 over x minus 3. That's basically the method of partial fractions. And obviously we can see the benefits of this method. You go from a much more complicated fraction to a bunch of smaller little ones that are easier to deal with. And especially when it comes to integration, this can be very convenient. So let's jump to some examples. I'm just going to jump to 10. So for these, I just want you to find the partial fraction decomposition, and then we'll actually do some integral problems. Squared plus 3x minus 26 x minus 4 We're going to find the partial fractions of all those guys. Let's look at A.
Long division.
Long division. You look at that, the power on top is higher than the power on the bottom. So we have to do either long division or maybe some other manipulation. So we can do x minus 4 out here, x squared plus 3x minus 26. X into x squared goes x. X times x is x squared. X times minus 4 is minus 4x. You subtract this from the top. That dies. 3x minus a minus 4x gives us 7x. Then you do everything over. X into 7x goes 7. 7 times this gives us 7x. 7 times minus 4 gives us minus 28. You subtract that. Now you have minus 26 plus 28. The 2, which is your remainder. So now you would end up with x plus 7 plus 2 over x minus 4. And basically that can't be broken down any further. That's a pretty nice one. Right? The denominator here can't be factored, so we pretty much stop. So if I actually integrate this, you'd actually just integrate that, which is pretty easy. So we didn't have to go through the method for that one because it just didn't work out that way. What about B though? 5x squared plus 20x plus 6 over x cubed plus 2x plus x.
It's 2x squared. It's 2x squared.
2x squared. So what's the first thing we check though? The degrees. Degree of the top is 2, which is the degree of the bottom is 3. The top is smaller than the bottom, which is good. Now we can move on with the method. Factor the denominator. So 5x squared plus 20x plus 6. What's the factor of the denominator? X squared plus 2x plus 1.
X plus 1 squared.
That's x plus 1 all squared. Alright, so we have to factor completely. This is x times x plus 1 all squared. How do we break that up? A over x plus b over x plus 1 c over x plus 1 squared. At this point, what do we do? Multiply both sides by this denominator. So I get 5x squared plus 20x plus 6 equals, multiply by this, the x's would cancel. I just have ax times x plus 1 all squared. B, I would have bx times x plus 1. C, I would have cx. Right? At this point, can you think of any convenient values? Negative 1 and 0 seem pretty convenient. Let's do negative 1 first. Plug in negative 1 here. What do I get? I get 5 minus 20 plus 6. On that side, if I plug in negative 1, I kill this, I kill this. I just have minus c. Right? So c is equal to what? Negative 9. Well,
It's negative 9.
it's negative.
15.
No, wouldn't it be 9?
It's negative 15 plus 6. It's negative 15 plus 6 equals negative 9.
Okay, we're tired. Right, 5 plus 6 is 11. Minus 20, minus 9. You have minus 9 equals minus C, so C equals positive 9. Okay. So C is positive 9. Okay, we found C. We're going to have to erase this. What about the others? Well, we already knew another convenient value. If x equals 0, what happened? This cancels, I'm just left with a 6. What happens to the a? I just become a, right? Because x is 0. This would die, that would die, right? So a equals 6. What about the third guy? So at this point, there's no convenient value. But also, I don't really want to, not in the mood to expand anything. You can actually just plug in these two values. Plug in what you know for A, plug in what you know for C, and plug in any random x value. Right? Ideally, you plug in one that's small. You don't want to have big numbers. So minus 1, 0, the next smallest thing was 1. I'd probably try 1. Right? And then I would have 5 plus 20 plus 6. That gives us what? 31? Sounds like 31. Okay, and then what would I have here? A is 6, right? Plug in a 1 here, so that's 6 times 4. Plus B, do we know B? No, we don't know B. So it's B times 2. And C, we know is 9. So it's plus 9. Right? So this is, the 6 is the A that I plugged in. This is the C that I plugged in. And with that, we can actually solve for the B, right? So
B is negative 1.
B is negative 1. At this point, not sure if I can trust you guys with that, but okay, guys.
I'll use the calculator.
What does the world come to? So at this point, it means that this guy, 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x is actually equal to a over x, my a is 6, b over x plus 1, my b is minus 1, and c over x plus 1 squared, and my c is 9. And of course, if you were to integrate this, this would be trivially easy. What is the integral of this? 6 ln of absolute value x, integral of this? Right, minus ln of absolute value x plus 1, integral of this?
You know. We've done this.
Yeah, we've done it. What is the integral of that?
Power rule, you take it to the power negative 2.
Right, and?
Then you just plus 1 and then this is that. You know, power rule.
Technically you have to do a substitution, right?
Yeah.
So it's like a u x plus 1, but the derivative here is 1, so you don't worry about it. So yeah, it's going to be minus 9 over x plus 1. Right? If your inside was like a 3x plus 1, you have to multiply by a third, etc. You have to remember that you have to multiply by that. Okay. So yeah, we have to integrate this. It's trivially easy. We'll just edit that part out. What was my next example? C. Two x cubed minus 4x minus 8. X squared minus x times x squared plus 4. What's the degree of the top? 3. Degree of the bottom? It's 4, right? When you multiply out, you get x to the 4th. So the power on the bottom is bigger, that's good. So we can actually continue with our method. Is the bottom factored completely?
No.
No. X cubed minus 4x minus 8 over, what's the factor?
X times x minus 1.
X squared plus 4 cannot factor over the real numbers. And so we have this. So at this point, we can start to break things up, right?
Yeah.
What would we get?
A over x plus b over
Plus b over x minus 1 plus cx plus d over x squared plus 4. This means you multiply both sides by the denominator over here. I get 2x cubed minus 4x minus 8. Now, hopefully I have space for this. The x is going to cancel. I'm going to have a times x minus 1 times x squared plus 4 plus b times x squared plus 4 plus cx plus d times x minus 1. Again, I don't too much fancy multiplying this out, so I wouldn't even think of method 2 really. But I'd start by trying to see, are there any convenient values?
One would be negative.
X equals 1 would kill this term and that term and leave me with just the b term, so that's pretty good. X equals 1 gives me what on the left side? What? What are we talking about?
Negative 4 plus 2, so we're negative 10.
Negative 10. On the on the right side, if I plug in x equals 1, the a term dies and the cx plus d term dies, and I just have the b term.
5b.
Oh, 5.
Right, I have 5b, and that's it. Yeah, we're gonna die with algebra. Arithmetic. Okay, so this means b is minus 2. So we found the b. Is there another convenient value?
Yeah.
0 is pretty convenient. If I use 0, I will kill the b term and the c term, cx plus d term. And on the left side, I would get minus 8. And the a would give me what? Minus 4. A. So my a is 2. Yeah, the rest of it isn't going to be so nice. Any other convenient values? There's nothing that will kill everyone except one guy. So at this point, just start plugging in random values. Try to keep the numbers small because we don't want to kill ourselves. What's another value you try?
Negative 1.
Negative 1. So on this side, what do I get? I get minus 2 plus 4, which is plus 2 minus 8. I get negative 6. On the left, I have a, which I know is 2. And my x is negative 1, right? So it's negative 2 times 5 plus b, which I know the answer to. b is minus 2. X is negative 1. X squared plus 4 is 5 plus minus c plus d times minus 1 times minus 2. Right?
So 4 equals to negative c. Okay, never mind. No,
Did you just make that up?
No, I calculated that.
This is minus 20. This is plus 10. Mine plus 2. 2d minus 2c.
Why don't you just divide everything by negative 2?
Could divide everything by negative 2.
Yeah, do like 2 both sides.
Okay, and then what?
Negative 3.
So like negative 3 equals negative 10.
Negative 3 equals,
So wait, no, what's it, negative 10? So negative 10?
this would be d minus c. This would be negative 10, but you divide by 2, so it's negative 5.
5 plus, yeah.
And then you move that over, so what do we get?
2 equals.
2 equals to d minus c.
Whoa.
Okay, so at this point we can't really do anything, so we hold it there. All we need is now one more equation, right? We have 2 unknowns, we need 2 equations to solve it. So now we need one more value. What do you want to plug in?
1 million.
Of course. Obvious. What do you want to plug in?
2 minus
2, right? Very small, positive. And on the left side, what do we get? 16
16 minus.
minus 8 minus 8. So it's just 0 on the left side. Not bad. And then I would have a. I know what my a is. That's 2. I'm plugging in x equals 2 here.
1.
So I get 1
But 8.
and 8 plus, do I know the b?
B is negative 2.
b is negative 2. My x is 2.
Plus 8 again.
And this is 8 plus my x is 2, so I have 2c plus d
16 minus 8
times 2 times 1. And again, I can divide both sides by 2. So what I have is 0 goes to minus 16
and C.
plus 2c plus d. So this means that 16 is equal to 2c plus d.
And then C.
And
C plus D plus.
let's call that equation 1. And I know that 2 is equal to minus c plus d. That's equation 2. Let's subtract this minus that.
Or can't we just say like C equals D plus 2 or something like that? Like, no? No?
Well, c would be d minus 2. You could do that.
Yeah.
So if you subtract these, if I say take 1 minus 2, what do we get? 16 minus 2?
14.
2 minus
C.
3. And then that dies. So c is actually 14 over 3. And so this would mean, let me use the 0. There was, what equation? We can use any one of these equations. Right, so let's use the smaller one. 2 equals minus c plus d, which means my d is equal to what? 2 plus 14 over 3. 2 is actually, what?
6 over 3. So
2 is 6 over 3 plus 14 over 3.
20 over 3.
So 20 over 3 equals d. And yes, it's possible to get ugly numbers like fractions. Calculators are not allowed. So we have everyone now. So the original was,
Wait, why would
we're doing this because we might want to integrate someone that looks like this. What would it break up into?
So A is 2. So
It was a over x,
2 over x plus
Minus.
b was negative
So
2,
negative 2 minus.
and the c,
Plus 14 over 3x.
14 over 3x
Plus 20 over 3.
That's 20 over 3.
plus 20 over 3
Above x, but x squared plus 4.
all over x squared plus 4.
Let me integrate that.
Yeah.
And the third one.
These are two ln's. How would you integrate this one?
And those one you have to do again. Oh, wait, can you wait,
Huh?
that'll be 2x. How are we supposed to do?
How would you integrate this one?
That's not. We split it.
You split it. Split it into this and that. The first one is a u sub, the second one is an arctangent.
It's not. Minus 3 over 2.
How much time?
Never mind.
We're 1 minute. Let's do the other one. We'll stop right there. We didn't finish the section. I have a few more examples. I have one. Well, there are 2 we didn't do. 3, 4, 5, 6, 7, 8, 9. Lots of examples.
No quiz on Monday?
Of course, there's a quiz on this.
But there's